we can use the 2016 paper Spot the Physics Theory, where we have some of the ideas and subject matter in binary mechanics conveniently summarized. Table 1 features some first principles. The tables compare and contrast what we have in binary mechanics with what we see in the standard model and legacy physics, what you're going to see in your textbooks, basically. Let's start with the continuous space-time assumption. Yes, in classical physics, this tradition is honored all the way up to the standard model. In binary mechanics, it is thought that this has no known justification other than tradition and superstition. So what do? We've quantized space, time, and energy, full energy quantization. In the classical regime, we have the smallest length is supposedly the Planck length, and the smallest time, the Planck time. And as far as energy goes, we only have Planck's constant h, which is actually a product of energy times seconds, and it's called an action. And so it's not exactly an energy quantization separate from time or frequency considerations. However, in binary mechanics, we have only 1 and 0 state bits allowed. Here are the primary constants as they're now denoted with capital M, L, and T, and their values that we think they have, with energy, space-time, quantization, the primary constants. All the rest of it are secondary constants. Quantum theory consists of two main questions. First, what do we have? It could be an electron or an atom, a whole galaxy, the whole universe, and how do we define that mathematically? And the second question is, how does this system, what we have, change with time? What we have is called the system state and is the bit function in binary mechanics and the wave function in the standard model. The bit function is superior to the wave function because it can represent both position and momentum at the same time, whereas the wave function can only represent one or the other, position or momentum. And the mathematical representation is the spot unit consisting of two binary bits, which can only have 0 or 1 states, to quantize energy, assembled into groups of 3 called spots. And these spots then are assembled into the mathematical model of space called the spot cube, which consists of 8 elementary particles. Once we define what we have, the system state, mathematically, then we need to determine how it changes over time. In binary mechanics, we have the 4-bit operations. In the legacy physics, we have inapplicable infinitesimal operator math. It is inapplicable because we have quantized space and time. So the system state time evolution precision is exact mathematical formalism in binary mechanics, whereas only event probabilities are available in the legacy physics regime. The momentum operator, yes, we have it. It's called the unconditional bit operation derived or based upon features of the relativistic Dirac equation. The primary forces, we have 3 in binary mechanics: electrostatic, magnetic, and strong, whereas there's 4, 5, or who knows how many in the standard model and legacy physics. Why? Because they're looking at particle interactions, which is a very chaotic, non-systematic way to define forces in physics. The primary force definitions are exact mathematical formalism in binary mechanics, whereas in the past it was based upon particle interaction categories. The primary force definition consists of 3 points: the 1-state bit in a source locus, secondly, an adjacent 1 or 0 state bit in a potential locus, third, related to special relativity, is a 0 state bit in the destination locus. If a 1-state bit is going to move from a source to a destination locus, the destination locus must be empty or in the zero state, which is related to neutrinos, by the way. On the other hand, in classical legacy quantum physics, we have point-like particles involving illogical, incoherent math, and the potentials are a virtual zoo, charge, mass, etc., and the legacy continuous space-time math is used. Notice that the distance between the one-state source bit and the adjacent potential bit is primary length constant L, called D in this particular table. So yes, we have in binary mechanics action at a distance, and that distance would be our primary length constant up to light speed reach, whereas in legacy theory, we have any distance within light speed reach. Gravity and weak forces are secondary, not primary, in binary mechanics, but are mostly considered by physicists today as primary forces, both of them. With regard to singularities and infinities, no, because we're only defining selected points. We have singularities and infinities because legacy theory attempts to define all points. Mathematical self-consistency, yes, and that means that physical models are possible. Whereas in legacy theory, things are infinitely small because they're attempting to model all points, and so infinitely small things are nothing, so there's no physical models possible. So yes, we have finite-sized objects and physical models are possible, whereas in legacy physics, the math says that objects are infinitely small, so you can't have physical models. And physical models involve field encoding and operator mechanism. In binary mechanics, we have the EM and strong potential fields, whereas in the past, the encoding devices are infinitely small, so they don't even exist. The operator mechanisms, yes, we have the bit operation defined, but in legacy theory, the operator mechanisms are proposed, but they're infinitely small, so they actually don't exist. How about properties of particles such as their charge, color, helicity, and direction, etc.? All of these are derived from the three XYZ spot coordinates. We have 0 or 1 for Y, and X and Z, and these coordinates within a spot cube define all of these physical properties. It's sort of an amazing accomplishment when you think about it. Whereas we have a virtual zoo of legacy mathematics in legacy quantum theory. How about magic? A form of entertainment? No, in binary mechanics we have science without magic, whereas it's required in the legacy theories, for example, a sea of virtual particles on demand. How about religion? No, we think that religion might be okay, but we don't need it in physics. So we don't have miracles. Physically, a point equals nothing. We do have religion in legacy physics because the math asserts that nothing is something. So we've touched on some things concerning the two main questions of quantum theory. First, what do we have? That's called the system state and how we define it mathematically. And second, how does what we have, the system state, change with time? And that involves the bit operations in binary mechanics. Now let's look at some predictions that result from space-time energy quantization.